So, last class we have discussed the methods for solution of first method. Different methods are there. First method is iterative method. So, you have given the what is called algebraic Riccati equation. That algebraic Riccati equation will arise in case of infinite time regulator problem. Agree? So, this is the algebraic Riccati equation. So, this term and this term we club together, again P into A, this one, P into B R inverse B transpose P, there is another one additional term is added with a negative sign. So, with positive sign we have used here P B R inverse B transpose P. So, this and this cancelled. So, this will remain same as the previous equation. So, this we have written it like this way. Now, we have introduced some P, we have introduced P of suffix k, means value of the P matrix at kth iteration, and outside this bracket is this one P k plus 1, value of P at k plus 1th iteration. Knowing the value of P at kth iteration, we can compute the value of P at k plus 1th iteration. So, we have written into like this way. So, in order to solve this equation, it is a something like Lyapunov type equation that we come across in the solution of stability analysis of a autonomous systems. Means suppose you have a x dot is equal to a x and we want to study the stability of the system based on Lyapunov function, then we consider a energy function B in quadratic form x transpose P x. Then we this energy function is a positive definite function, positive semi definite function, and we have to show for the system A to be stable provided B dot means rate of change of energy should decrease with time, that we have to show it, and that condition is that one A transpose P plus P A is equal to minus Q. So, this is called a Lyapunov type equation while we will study the stability of a autonomous systems. How to solve this one? That you assign the what is called Q is a positive definite matrix, then solve A transpose P P A, agree, for P you solve it. If P is a positive definite matrix, it indicates A matrix is a stable one based on the derivative of the Lyapunov function, we arrived this condition. So, here also we initial value let us call k is equal to 0. So, P of 0 you choose in such a way, so that A minus B R inverse B transpose P, it is nothing but a B k. If you recollect, k is R inverse B transpose P. So, it is B k, and you have to, I told you you have to select P of 0, k is equal to 0, in such a way this matrix is stable. So, it is A transpose A C transpose or whole matrix I can write A k is nothing but a closed loop system matrix at kth iteration. So, it is A k transpose P k plus P k plus 1 A k, this is A k is equal to Q P k P B R inverse B transpose then P k. So, I know P of 0 I have assigned initially in such a way, so that A minus B R inverse B transpose P k is 0 stable. So, since this is a positive definite matrix, Q is a positive semi definite matrix, result will be positive definite matrix, and if the resultant is this positive definite matrix, we know that A minus B R inverse B transpose P k is the stable one. So, if you solve this one, then we will get P k plus 1, k plus 1th iteration, the P value will be positive definite. And next is, once I know from the knowledge of P 0, if I can compute P 1, then use the P 1 in this expression A minus B R inverse B transpose P, P is P 1 now. You find out P of 2 by solving the Lyapunov equation, and in this process you go on solving recursively until and unless the P converges to a some constant value. So, next is remarks, we can just write it. The initial choice of P if you recollect that what I told you, the initial choice of P 0 should be such that A of 0 is equal to A minus B R inverse B transpose P of 0 is stable. Agree? So, at any iteration, any kth iteration, I can write A of k is your 0th iteration A 0, kth iteration A k is equal to A minus B R inverse B transpose P k, and k is equal to 1, 2, 3 dot dot in iteration R. So, is stable. Initial choice is such that it is stable. Subsequently, you can write it that subsequently it can be shown that all matrices this for k is equal to 1 to 3 A k are stable. And next observation we can see it rather P k plus 1 is less than equal to P k. That means, this P k minus, in other words you can say P k plus minus P of k, this matrix is less than equal to 0, means this is a negative definite matrix. That means, in other words I can say the P k plus 1 is less positive definite than the P k. Agree? Then I can write third one is limit k tends to infinity. The iteration, if you go on increasing in the like this way recursively, if you solve it the Lyapunov equation, then you will see P of k will equal to P, which is a constant. It converts to a constant matrix. So, only things is when you will start the iteration, you have to select P of 0 in such a way A of 0 is stable, and then start recursively solving this one until unless that P k plus 1 and P minus P of k is less than equal to norm of this one is less than equal to some pre specified values. Agree? Small values are there, or when P converts to a some constant value. So, this is the this method, in this way we can solve the Riccati equation, algebraic Riccati equation, that is called iterative method. But one disadvantage of this method is that if your initial guess is not appropriate, then it will take longer time to converge the solution of the Riccati equation P to a constant value. This is the one of the disadvantage of this method. So, next method is a eigenvalue eigenvector method. That means, based on the concept of eigenvalue and eigenvector, one can find out the solution of algebraic Riccati equations. Agree? So, method 2 is based on the eigenvalue and eigenvector method. That means, solution of the algebraic Riccati equation based on eigenvalue eigenvector method of the Hamiltonian matrix. So, first step 1. So, first you all the when you are designing a LQR problem, first check it is there, you have to see whether the system is controllable or not. So, the controllability test we have already mentioned it here. So, just mention first check the controllability of the system. Agree? That means, if your rank of B A B dot dot A n minus 1 B must be equal to n. N is the number of states or the order of the systems, and B is the input matrix, A is the system matrix, the rank of this matrix must be n. If it is a n, then we will call system is completely controllable, means all the states we will be able to from initial state we will be able to drive the state at desired state with a finite control actions, agree, in a finite time. So, this is the thing. If this fails, then this program will show the error message, that means we will not be able to design the LQR problems. If the system is not controllable, return with an error message. The error, this message will be there that we will not be able to design a LQR controller for these systems. Step 2. So, form the Hamiltonian matrix and to form the Hamiltonian matrix, if you recollect, we need the information A matrix, B matrix, Q matrix and R matrix. So, A minus B R inverse B transpose, then Q minus A transpose, and this is the Hamiltonian matrix. And this Hamiltonian with how we have formed it, if you recollect that x dot of t and lambda dot of t, this is the co-state vector, it is the base state vector, this equal to h m into x of t lambda of t. So, this is the augmented state vector with state vector and the co-state vector, and each dimension, this dimension is 2 n cross 1, this dimension is 2 n cross 1, 2 n cross 1, if you see this one. Now, this we form the Hamiltonian matrix, this Hamiltonian matrix dimension 2 n cross 2 n. So, this is the so this matrix have a how many eigenvalues are there? There are 2 n eigenvalues are there. We have shown it analytically that this matrix having a set of eigenvalues, that means n eigenvalues are in the left half of the S-plane, and or you can say n eigenvalues are with negative real parts and remaining n eigenvalues are the right half with a positive sign, eigenvalues with a real positive sign. That means, n eigenvalues are stable eigenvalues and n eigenvalues are unstable eigenvalues, and they are symmetric about the imaginary axis. So, these are the Hamiltonian matrix and all its eigenvalues are, let us call, we have defined the eigenvalues are mu 1, mu 2, mu 3 dot dot mu n, and another set of eigenvalues will be minus mu 1, minus mu 2 dot dot mu n minus this one. We have seen it that Hamiltonian matrix, there are two sets of eigenvalues, they are symmetric about the imaginary axis of the complex plane. So, that is, let us call this set of eigenvalues are the stable eigenvalues, of H m Hamiltonian matrix, and these are the, since this is, if this is the stable, since it is a preceded with minus, that will be unstable, because this stable means the eigenvalues, the real term with a negative sign, if it is a stable one, a negative sign, and there is a preceded with negative means positive sign. So, the eigenvalues real values of the these eigenvalues are with a positive sign, that means unstable eigenvalues of H m Hamiltonian matrix. So, so this positive real parts, this is the negative real parts, positive real parts of eigenvalues, real parts of eigenvalues, negative real parts, then this will be positive real parts of eigenvalues of n. This n eigenvalues are there. So, this we have just defined this one. Then if you that we will just see this one, that eigenvalues are symmetric about the imaginary axis or the symmetry about the imaginary axis. To show this one, we have already discussed this one earlier. At this stage, we just briefly discuss how we are making comments like this way. Their eigenvalues of Hamiltonian matrix are symmetric about the real imaginary axis. So, do the similarity transformation, similarity transformations. So, let us call x of t, lambda of t, this co-state vector augmented vector of this one, we have used the transformation like this way. So, let us call this is the equation number, we are just this equation, let us call equation number 1. Okay, this is the equation number 1. From equation 1, or you can say equation 1 can be rewritten, equation 1 can be rewritten as that x dot. So, it is a I, this is a constant matrix P I, then your x bar dot of t, agree, then lambda bar of t, lambda bar x dot lambda dot is equal to this into x bar dot lambda bar dot, this equal to, we are writing, we have a Hamiltonian matrix H m, then we are writing for this one I, then 0 P I, this into h bar of t, lambda bar of t. Agree? So, this we can write it for this one, that what is H m? We know the H m expression, then we can write it left hand side, lambda bar of t is equal to lambda x bar of t augmented with a lambda bar of t, this equal to I 0 P I whole inverse, then our Hamiltonian matrix. If you write the expression for Hamiltonian matrix, this is nothing but a B R inverse B transpose, that is minus q minus A transpose multiplied by then your I, just I have simplified that one. X bar of lambda bar of t. So, if you use the matrix inversion lemma of this one as we discussed earlier, and if you do it after simplification, we will get the final results is like this way, A minus B R inverse B transpose P, and this is nothing but our k. If you see, this equal to minus B R inverse B transpose, that equal to, that side is equal to A transpose P plus P A minus P B R inverse B transpose P plus Q, and that will get minus of that matrix A minus B R inverse B transpose P, this equal to x bar t lambda bar of t. So, if you just multiply from here to here, you will get this matrix. So, now see this one, this is the algebraic Riccati equation, this quantity is equal to 0 for this one, okay, and this one is 0. So, it is nothing but an upper triangular structure. upper triangular, and this is nothing but a closed loop system matrix, and the closed loop system matrix is stable. It is enough if you consider that Q is a positive semi definite and R is a positive definite matrix, then this is a stable one. If it is a stable one and this is preceded with a minus sign, so this will be a unstable. This matrix eigenvalues are unstable. So, this matrix whose dimension is n cross n, this dimension n rows, this is n columns. Similarly, this is n columns and this is the n rows. So, n eigenvalues of this is stable and this block eigenvalues are unstable. So, whole system eigenvalues after transformation, we know the eigenvalues does not change, it only eigenvector with similarity transformation eigenvector will change. So, since it is a block diagonal matrix, the eigenvalues of the whole matrix is nothing but eigenvalues of this block, which is the stable eigenvalues, and eigenvalues of this block, which is the unstable eigenvalues, because of that minus sign is preceded with that matrix. Okay. So, that we have shown it earlier also here also. Now, see that this is the second step. If you just see the first step is you will check it the controllability test. If the system is controllable, then go the second step. In second step, you just form Hamiltonian matrix, and other things what we have discussed, just to show the Hamiltonian matrix eigenvalues. There are 2 n eigenvalues are there. N eigenvalues are lying to the left of the spline, in the sense the n eigenvalues with a negative real parts, and remaining n eigenvalues are positive real parts. They are symmetric about the imaginary axis. So, once you find out this HM matrix, then find out the step 3. Step 3, they find out the eigenvectors of the Hamiltonian matrix, find the eigenvectors of the Hamiltonian matrix corresponding to the stable eigenvalues. I repeat, I once again, find out the eigenvalues of the Hamiltonian matrix whose dimension is 2 n cross 2 n. You find out the eigenvector corresponding to the stable eigenvalues of H m. That is our next step. So, step A, let that V I U I whose dimension is V I dimension is n row 1 column, this is the 1 column, this is the n row, that means this dimension is twice n into 1. Let atho is the eigenvector or generalized eigenvector of the matrix H m corresponding to negative real parts corresponding to, or in other words corresponding to mu I. And what is mu I? The stable eigenvalues. What is stable eigenvalues? The eigenvalues with negative real parts. Eigenvalues with negative real parts means this is the corresponds to stable eigenvalues, eigenvalue of H m, that is. So, you find out the eigenvector of that one corresponding to mu I. So, if you find out this mu 1 and you can find out, we know the our for I is equal to 1 2 dot dot n. You see this one I how many stable eigenvalues are there? We have a n stable eigenvalues are there, n unstable eigenvalues are there. We are concentrated, or we are our attention to find out the eigenvector corresponding to n stable eigenvalues of H m. So, for I is equal to 1 to n. So, the solution of the proof we will give it later, the solution of algebraic Riccati equation, then one can find out, that means this solution A transpose P A minus P B R inverse B transpose P plus Q is equal to 0. The solution of this one is obtained as P is equal to that you form a U 1, U 2 dot dot U n, then this matrix B 1, B 2 dot dot V n whole inverse. Now, see this one. Which one? That 3, 4. Now, see this one here. This is the eigenvector corresponding to eigenvalue mu I, which is stable eigenvalues. And when you are getting the first n rows of this column vector, you partition as a V I. Remaining n rows of this vector, you partition as a V I. So, since we have a what is called n stable eigenvalues, the first partition and first n rows I am writing V 1, V 2, V 3 dot dot V n, and remaining last n rows of the eigenvector corresponding to stable eigenvalues I am writing U 1, U 2, U 3 dot dot U n. So, the solution of the Riccati equation of this one. So, this is the stable eigenvectors of H m corresponding to U 1 corresponding to mu 1, agree. Last n rows of these eigenvectors is U 1, the last n rows of the eigenvector corresponding to mu is equal to mu 2 is the U 2 and so on, and this is the first n rows of the eigenvector corresponding to stable eigenvalues mu 1. This is stable eigenvalues mu 2, first n rows of the eigenvectors in this way. So, if you compute this, that will give you the solution of the Riccati equation. So, this dimension, if you see how many rows are there, n rows, this is column 1, in this way we have a n columns are there. So, this dimension is, if you see this dimension n cross n, this dimension is n cross n, and this inversion is exists because eigenvectors of that one comprises that one V 1, V 1, all these things. So, let us see the proof of this one. So, these are the eigenvectors. What you can write it for this one? If you see that one, this what is called, this is the closed loop system eigenvalues, closed loop system matrix A minus B R inverse B transpose P is the closed loop system matrix. So, this way you can solve it this one. So, let us prove that how we are getting this expression. So, proof. So, algebraic Riccati equation we rewrite here, algebraic Riccati equation A transpose P plus P A minus P B R inverse B transpose P plus Q is equal to 0. Let us call this is equation number 1. This equation we are writing into different form. Look, mu I is the eigenvalues of the matrix, Hamiltonian matrix corresponding to a stable eigenvalues mu I. This is I have added with A transpose multiplied by P A transpose. So, this is more, one term is added, that is subtracted like this way, mu I agree, then A minus plus B R inverse B transpose P plus Q. Let us call this is equation number 2. Now, say mu I P minus P mu I, agree, that if you multiply it by this one, mu is a scalar quantity, agree. So, this and this cancel. So, A transpose P minus, and that is a minus, plus P A, that minus, this plus, minus P B R inverse B transpose P plus Q. So, it is same as equation number 1. So, now next is the eigenvalues. Let us go now, if the eigenvalues of A minus B R inverse B transpose P R mu 1 mu 2 dot mu n, and that corresponds to stable eigen values. If the eigenvalues of this matrix are mu 1 mu 2 this agree stable eigenvalues, then we can write by definition of eigenvalue and eigenvector, the definition A B R inverse B transpose P, this into that vector is V I. Let us call corresponding to this vector, this is the eigenvalues corresponding to these vectors are V I. V y I is equal to 1 to n, then V 1 V 2 is the eigenvectors corresponding to this matrix. So, this plus is equal to that mu I into V I. This is the definition of eigenvalues eigenvector. This is the matrix and closed loop system matrix that eigenvalues are mu 1 mu 2, which are the stable eigenvalues we are considered. So, by definition of eigenvalues eigenvector, I can write it closed loop system matrix into corresponding eigenvector if it is V I must be equal to mu I into V I. So, this I can write it after bringing it in this side B R inverse B transpose P, this minus you bring it mu I whole V I is equal to 0. Push it P V I in the inside. So, it will be V I minus P B R inverse B transpose P V I again minus mu I V I. So, if I take it right hand side, it will be mu I V I. So, this is nothing but a V I minus P B R inverse B transpose, that is called this matrix, this will be a matrix multiplied by a vector. So, it will be a vector which I am denoted by U I is equal to mu I V I. So, let us call this equation is equation number 3, and this is valid for n number of equations. Okay. So, this is the one equation 3 you get it. Now, if you multiply it by this equation 2 by V I post multiplied by V I both sides, then what will get it? This equal to that is this equal to 0 null matrix. From equation 1 you see we have adjusted this equal to right hand side null matrix. So, here I missed it, it is a null matrix here. So, I multiplied by equation 2 multiplied by V I, then what we get it? Let us say mu I plus A transpose P V I minus P, that is V I. See equation 2 V I, that means I, then minus A plus B R inverse B transpose P multiplied by V I plus Q V I is equal to null matrix. Now, look at this expression you see this expression, what you can write it A V I, if you multiply by A V I, you see this one A V I B R inverse B transpose U I minus mu I V I is equal to 0. If you take this one this side, it will be 0. So, if you see is here, then A V I R inverse P V I, then mu I, but it is a minus with this one. So, this quantity is 0, this quantity is 0. So, I can write it now mu I plus A transpose P V I agree. Then I am taking the minus sign common, it will be plus A minus B R inverse B transpose P V I agree, minus, this is the minus sign, if I take it common, this is plus. So, it will be a minus mu I V I plus q V I is equal to 0. So, this quantity form equation 0 from 3. So, you got it this one, this is nothing but a u I. So, you got it mu I plus A transpose u I plus q V I is equal to 0 and I is equal to 1 2 dot dot n. So, let us call this is equation number 4. Now, you just write from equation 3 and 4, from 3 and this from equation 4, we can write from 3 and 4. Note V I is the what? If you recollect, V I is the eigenvector of the matrix, closed loop system matrix corresponding to a eigenvalue mu I, corresponding to eigenvalue mu I. This is the eigenvector, and mu I is the, what is mu I? Mu I is nothing but a the stable eigenvalues of Hamiltonian matrix, that is. So, from 3 and 4 we can write it A minus B R inverse B transpose minus Q minus A transpose. This is the Hamiltonian matrix, and this equal to V I U I, then is equal to mu I and V I U I, and that is for I is equal to 1 2 dot dot n. So, let us call equation number 5, and these are the what? This is, if you see, this is the eigenvector. This dimension is what? If you see, this dimension is, this matrix dimension 2 cross 2 n, and this dimension is 1 cross twice n. This is the twice n. So, one row, one column, twice n. So, these are the eigenvectors corresponding to Hamiltonian matrix. Agree? This is the Hamiltonian. That what I told you earlier also. You find out the eigenvectors of the Hamiltonian matrix corresponding to the stable eigenvalues of H m, means Hamiltonian matrix, and then you can find out the what is called solution of algebraic decay equation. This, and this is, you can write it eigenvector of H m corresponding to, by definition of eigenvalues eigenvector, you see A x is equal to lambda into x, the eigenvector corresponding to mu I, which is a stable eigenvalue of H m. This is or you can say stable eigenvalues of A minus B R inverse B transpose P. This is the stable eigenvalues of, this is the stable eigenvalues of this matrix also. Agree? This matrix also. So, now this I can write it now from. So, we know or we have defined, you see, P V is equal to U I and I is equal to 1 2 dot dot n. So, I can write it P V 1 V 2 dot dot V n is equal to U 1 U 2 dot dot U n. Augmenting the I is equal to 1 to n, these matrices are, these vectors are augmented like this way. So, this is nothing but a, this dimension is n cross n, because this is the row is n rows, this is the column 1, this is the column 1. So, we have a this is also n cross n. So, therefore, P is equal to U 1 U 2 dot dot U n divided by that was inverse of post multiplied by this one V 1 V 2 dot dot V n whole inverse. Mind it that V 1, V 2, V 2 is the eigenvectors of the matrix, eigenvectors of the matrix A, B, R inverse, V transpose P, closed loop system eigenvalues, eigenvectors of this one. These are the eigenvector of this matrix, eigenvector of this matrix corresponding to the eigenvalues mu I, corresponding to eigenvalue mu I. Since these vectors are, it can be proved that V 1, V 2, V 3 dot dot V n is the set of eigenvectors corresponding to the set of eigenvalues mu 1, mu 2 dot dot mu n, that is the n eigenvalues are there, they are linearly independent. So, the inversion exists for this one, agree. So, this way you can, one can get the solution of this one. So, if you summarize this one, then what is the step to solve the algebraic recurrent equation? First you check, first step is you check whether the system is controllable or not. If the system is controllable, then proceed second step. If it is not a controllable, send a message that this we cannot design a controller based on LQR. That means, solution of Riccati equation is does not exist, or we will not be able to stabilize the systems. Second step is here that you form a Hamiltonian matrix, and once you form a Hamiltonian matrix, then you find out, you can immediately find out, because you know a Hamiltonian matrix is known to you completely, because you know A, you know B, you know Q, and you know R. So, Hamiltonian matrix is known to you completely. Then you find out the eigenvalues of this matrix and consider only the stable eigenvalues of the Hamiltonian matrix, and find out the corresponding eigenvector of the Hamiltonian matrix, agree, corresponding eigenvector of the Hamiltonian matrix corresponding to the stable eigenvalues, agree. And once you got the eigenvectors of the Hamiltonian matrix corresponding to stable eigenvalues mu 1, mu 2 dot dot mu n, then first n rows of this vector you picked up, that is we denoted by V I, and remaining n rows or last n rows you denoted by U I. Then you form a matrix like this way, take the inverse, then this will be the solution of the Riccati equation. That is the proof of that one. But this this is our method what we have considered. This is the eigenvalue and eigenvector method. This method is numerically is not much sound, in the sense when you are finding out the eigenvalues or eigenvectors, and when the eigenvalues are the repeated eigenvalues, then we have to look for what is called generalized eigenvectors, and computation of generalized eigenvector may create what is called numerically some problems, can be not it is not reliable much to when we will compute the eigenvectors by this method, ordinary method. So, the next method is numerically stable methods. Method 3 is the numerically more stable method while we will computing the eigenvectors of the Hamiltonian matrix corresponding to stable eigenvalues of H m in Hamiltonian matrix. So, this method is called sure method to solve A.R.E, algebraic Riccati equation, and this sure method is based on QR decomposition method, agree, and that is numerically, that QR decomposition method is numerically stable or more reliable when you will compute the eigenvalues of the eigenvectors of this matrix, when the eigenvalues having a repeated eigenvalues are there. So, one can see the reference of this one, it is a good paper, you can see a sure method for solving algebraic Riccati equation, that appeared in IEEE transaction AC volume 24, number 6, June issue, and 1979. Even though it is a very old paper, but it is a basic things is given here only, and page 119 to 92, 121. Author is Alan J. Lamb. So, we will just briefly discuss the solution of this Riccati equation, algebraic Riccati equation based on what is called the Schur complement, means Schur method. So, step algorithmistic steps. So, step 1, but in this method what we will do it, we will just find out the eigenvectors of the matrix H m corresponding to stable eigenvalues mu 1, mu 2, dot dot mu 1, that is the method only. Once you know the eigenvectors of this one, we know how to find out the solution of the Riccati equation P, that means first n rows we picked up and will form V 1, V 2, V 3, V n, and this is nothing but the eigenvector corresponding to closed loop system eigenvalues. Agree? And the remaining n eigenvalues that of this Hamiltonian matrix eigenvectors, that eigenvectors such that 2 n cross 1 eigen dimension. The first n rows is denoted by V 1 and the remaining n rows, that means last n rows is denoted by U 1. So, from that information we can find out the solution of P, and in this method Schur method is giving the computation of eigenvector corresponding to eigenvectors of H m corresponding to eigenvalues, stable eigenvalues mu 1, mu 2, mu n. So, first step is form Hamiltonian matrix. H m is equal to A B R inverse B transpose minus Q minus A transpose. This is the equation number 1, whose dimension is n cross twice n into twice n. This step 2, with the help of QR algorithm, the matrix H m is transformed into upper Schur form. What is the upper Schur form? First structure is the S is equal to W transpose H m of W, and W is the orthogonal matrix, And orthogonal matrix means if we inverse of this matrix is nothing but a transpose of that same matrix. This is orthogonal matrix, and orthogonal W transpose is equal to identity matrix. That is the properties of orthogonal matrix. So, this is the orthogonal matrix, and the structure of if you look this expression, this dimension is H n dimension twice n cross twice n, and this orthogonal matrix also dimension is twice n into twice n, this, because this dimension is twice n into twice n. Agree? So, the structure of S, you will get it S 11, S 12 dot dot S 1 k, S 22, S 23 dot dot S 2 k, and in this way if you just go on S k k. So, this whole matrix dimension twice cross twice n, just like here this dimension of this one is also twice n into twice n, this orthogonal matrix. Now, what you will do it? You do the sequence of orthogonal transformation on H m such that the structure of S matrix, when you pre-multiplied by W transpose on W, the structure of P matrix will be this form, upper triangular structure. This will be a upper triangular structure, agree, this form. and look at this expression, each block either S11, S22, S233, 44, SKK4, KK, this block will be either 1 by 1 block or 2 by 2 block. This will be SII, where SII I is equal to 1 2 dot dot k is either 1 cross 1 means scalar or 2 cross 2 matrix. Okay. This will be the this matrix. So, this is the a sequence of orthogonal transformation we can make it on a HM matrix such that this matrix will be converted into this form either 1 by 1 block or 2 by 4. If the 2 by 2 block is coming in there, then this eigenvalues of that one S, you see eigenvalues, one can conclude the eigenvalues of A is same as the eigenvalues of HM, because you are doing the some similarity transformation. W transpose is nothing but a W inverse of this one, you can think of it like this way. So, eigenvalues are remain same. So, these eigenvalues are either it will be 1 1 this block or it will be 2 2 block, that means these eigenvalues will be either complex or real, this if it is a 2 by 2 blocks are there. So, now see how it is done it. So, this is just to get some idea that what we are doing it in this equation, that suppose given A, our problem is convert into a decompose A is equal to A into QR. Okay. So, let us call the matrix A is decomposed into Q into R. Q is a orthogonal matrix. And R is the upper triangular matrix, upper triangular matrix. Okay. Now, this is A is equal to this is the a matrix can be decomposed into this Q into R form. This can be done by using a sequence of orthogonal transformation, or in other words one can do a sequence of Householder transformation which will decompose a matrix into this Q into R. Let us call, we know how, we assume that this technique we know how to decompose a matrix Q into R. So, if it is so, then how will you get in Schur form into this form? A is equal to, I am writing is the given matrix A is written assigned with a 0 which is equal to our Q 0 R 0. Now, I have divided A 1. If you reverse the order of this one, because both are a dimension, if it is a n cross n, this each is n cross n, this is also n cross n. So, if you reverse this order, this matrix will be different from A 0 or A. So, this matrix I am now considering is A 1 is a R 0 Q 0. So, what is R 0? If you from here you take the inverse of both side. So, it will be a Q 0 inverse means transpose, because Q is a orthogonal matrix, Q 0 is orthogonal matrix. So, this will be this one into A 0 into Q 0. Okay. So, what is R 1? R 1 is nothing but a R 0 Q 0, and whatever the decomposition we do it Q 0 R 0, reverse order you write it R 0 Q 0 is A 1. Similarly, I can write it now A 2, that A 1 is just like if you decompose this matrix, if you decompose into a Q 1 R 1, I decompose in write the reverse order which is denoted by A 2 is equal to R 1 Q 1. So, what is our R 1? R 1 is nothing but a Q 1 transpose A 1, R 1 is nothing but a Q 1 transpose A 1 into, you see R 1 is nothing but a Q 1 from here R 1 value I am writing, R 1 value I am writing Q transpose A 1 multiplied by Q 1. Okay. So, what is A1? Just now you got it, A1 is this one. So, it is a Q1 transpose, Q0 transpose, A0, Q0, Q0, Q1. Okay. So, if we write it like this way, then I can write it is nothing but A2 is equal to Q1 transpose, Q0 transpose, A0, Q0, Q1 this. So, which is I can write it if you say Q0, Q1 whole transpose A0, Q0, Q1. Okay. So, next is what I will write it? I will write it A2, A3 is equal to, because this I can, this matrix A2 matrix I can decompose. A2 is what? I am written it into R1 into Q1. So, I can decompose this A2 is equal to Q2 R2. Agree? Q2 R2 I decompose this matrix, and how will you write it? This simply in this way, that Q2 is this, and what you can write it for this one after simplification in this way, then I am writing A3. A3 is Q2, A3 what we can write it? A3. Similarly, I can write finally Q0, Q1, Q2 whole transpose A0, Q0, Q1, Q2, and ultimately if you see, if you do the kth iteration AK, what you can write it AK? That Q0, Q1, Q2 dot dot Q minus 1 whole transpose A0, Q0, Q1, Qk minus 1 in this. Agree? So, ultimately it is nothing but a Q transpose A0 and Q. The two orthogonal matrix multiplication results is orthogonal matrix. Agree? So, it is something like this way. If you do this sequence like this way, ultimately I will get A is in the Schur form. Into Schur form means into this form, just like into this form, into this structure. This is all are zeros. That means either A1 S11 may be 2 by 2 block or 1 by 1 block. This may be 1 by 1 block or 2 by 2 block, but it cannot be more than 2 by 2 block. It is may 1 by 1 block or 2 by 2 block. So, ultimately if you proceed like this way, you will get it A k into Schur form. So, I just leave it, this is an exercise, please do it A to this one. Okay. This you just proceeded that one, and next class I will just complete the algorithm how to solve that algebraic Riccati equation using the Schur complement is Schur form, and Schur form is nothing but a numerically you are finding out the eigenvectors of Hamiltonian matrix corresponding to a stable eigenvalues, that is all only. Okay. So, we will stop it here.